Welcome to ECE Distinguished Lecture Series. Today is my great honor to introduce our first distinguished speaker, Dr. Bernie Myerson. Dr. Bernie Myerson is an inventor and innovator. He joined IBM Research in 1980. He's currently an IBM Fellow and Chief Innovation Officer leading technical strategy and corporate initiatives. He also serves as chairman of the World Economic Forum's Meta Council on Emerging Technology. Dr. Meyerson is a fellow of APS and IEEE, and a member of the National Academy of Engineering. He has received numerous technical and business awards for his work. In 2014, Dr. Meyerson was selected to present the Turing Lectures in the UK, and most recently was awarded the Singapore's National Medal for Public Service. Actually, I watched Dr. Meyerson's lecture online. The talk is very interesting, informative, and thought-provoking. He's really good at explaining complicated concepts using simple language that everybody can understand. I'm sure all of you will feel the same after today's talk. So without further ado, let's welcome Dr. Bernie Myerson.
All right, so here we get to do our first test. We're going to see if Microsoft works. That's always a thrill right there. In any case, the reason I have this image up, I think, well, some of you hopefully recognize this thing. Anybody know what that is? Right, SR-71 spy plane. It was also, by the way, going to be called a YF-12A. It was actually going to be a weapons system until they discovered anything you fired off of that thing while it was at speed came back and hit you in the teeth. Not all engineering is perfect, but the interesting thing is, this is a great example of what happens if you basically tell a bunch of engineers, go get them, and then you get the heck out of their way, because you see, they built this thing in about 18 months in technology that most of us would find primitive, and that's being very kind. It turns out it's the world's fastest airship. It certainly has held that record for a long time, but what was quite interesting is the record is not limited by the performance of the aircraft. What limits it is you can't radiate the heat fast enough to keep from cooking the pilot. So basically, unless you want your pilot medium rare, you have to actually tone it down. They did, you know, it's painted black. There's a reason for that, right? It's a black body radiator, sigma t to the fourth, very efficient. Yeah, it's still not enough to keep from cooking the pilot. So, you know, the best intentions, turns out it's much faster if basically you had it run by a machine than a person. But nonetheless, from an engineering point of view, it was nothing short of an astonishing achievement. And it does show that, you know, innovation can be a pretty amazing force if you basically let people do just their own thing, because they do it remarkably well. Now, what I want to talk about today, since there's a huge effort here, you know, engineering and such, I figured, well, let's talk about what's going on there, because it is quite fascinating. The world today is changing at such an incredible clip that it's hard, if you miss the changes, you basically cease to exist. You know, the number of companies that thought innovation was critical to their survival was about 55% if you ask the CEOs, about 10,000 of them back in, before the last economic crunch, you know, around 2007. By 2010, 80-something% felt that innovation is the most critical thing to survive. It's not that the numerator got any larger, it's just the denominator got a hell of a lot smaller. Anybody who wasn't innovating, they disappeared. It really is a driver of progress. And in a place like this, in a university, and this is where it comes from. Now, progress in technology itself has been really nothing short of amazing. I don't know, you guys know this, but when Kennedy said we're going to go to the moon, any sensible engineer would have run screaming from the room. Yes, I was around to listen to that speech. The interesting thing about it is that at that time when he said, you know, we're going to put a man on the moon in 1961, we had 2K of memory. For all the children in the audience, K is 1,000, you know. You guys are used to G, right? It's all, my kids basically tell me if it isn't a 64 gig, they're not interested. 2K of memory. How much programming do you really think you could do on 2K? The really thrilling part is by the time, and we did the IT for this in IBM, by the time we sent a man to the moon, we had 4K. It was a thrill. You understand, this is a whole different era because if you go forward to today, the average smartphone, between 2 and 64 gigabits of memory. So you've had about 62 million-fold progress. That's pretty good. But there is a limit, and that's one of the really dangerous things is when you look at this, one of the things we're all taught, is Moore's Law, right? And Moore's Law, you hear this to the point that it's quite distracting. I actually know Gordon Moore. He's a genius. The guys who came after him, not so much. Gordon basically had it right. He said, look, every 18 months what we put on a chip is going to double. That's, pretty damn good observation because it held for something on the order of 3.5, 4 decades. Not a lot of people make predictions like that hold across 6 orders of magnitude. But there's a catch. If you think about automobiles like chips, you'd be getting about 1 billion miles a gallon nowadays. Not likely to happen. Anytime somebody says there's an infinite extrapolation, your job is just, after you get them laughing, point out it doesn't work. Now, there are certain warning signs that it isn't working, and some of them are very subtle, some of them are very easy to spot. That's the other thing. By training, I'm a hardcore physicist. Solid state is my background. You do not have to be a deeply skilled scientist to tell when you're being bamboozled. By the way, that's the incredibly polite form of the word I was looking for. So here's a version of this that you may have not thought of. If you look at what went into a chip, when I started in this business, basically you had boron, phosphorus, your dopants, silicon, your semiconductor, aluminum, your metal, oxygen so you can make SiO2, your insulator, and hydrogen so you'd made a really loud noise if you screwed up the experiment. The point of it is, this is all you used in a typical manufacturing line to make semiconductors. Now, by the time 2005 rolled around, we'd done a few things. Titanium, tantalum, tungsten, these are metallizations we were doing, silicides to improve contact resistance. My team and I developed silicon germanium technology, made a lot of stuff, most people don't know. You know what our market share IBM's was in, for instance, Wi-Fi? About 100% for a decade or more. Sometimes basic science enables things. In our case, we enabled them to build the chips, some of them for a factor of 100 to 1,000 times lower cost. It's not necessarily about making it possible. You could do it in gallium arsenide or indium phosphide. It's just you couldn't do it economically. So in any case, this was the periodic table then. If you look now, what's been used to make a chip? Okay, if you see something that goes from this to that to this, you probably have a problem. This is, hello Houston, we have an issue. The bottom line is, what happened is people ignored the fact that the laws of physics are identical no matter whether you're on the east or west coast of the United States. Now on the east coast, since IBM was, we've certainly operated the leading edge of technology for many decades, we've been shrinking chips like everybody else did. But, if you're a physicist, you understand the idea of quantum mechanics, quantum, right? You can't shrink things forever. To begin with, at some point, if you draw a straight line, you actually get to the point you're below the atomic radius for the dimensions of your oxide. When you get below an atomic radius, that means you're doing nuclear fission to make the device. Let me know so I can get far away. And by the way, people were actually, it'll go on forever. No, it won't. Obviously, long before that, you get to 10 angstroms, 15 angstrom physical dimension gate oxide, and what happens is you now see quantum mechanical effects, and your insulator becomes a conductor. Which, if you think that's not a problem, stand in some water holding a hairdryer that's conductive. Actually, don't do that, please. Be a short and painful experiment. So, in any case, we saw this coming in the early 90s. It wasn't rocket science. You draw a straight line. There was actually a roadmap for oxide thickness, and you know the voltage, and you know the thickness, and you know when it goes quantum mechanical. Believe it or not, by 2003, where this was going to happen, nobody was taking any precautions. So I actually got permission from IBM senior leaders, since we'd already handled this, to give an open talk in San Jose at the Microprocessor Forum because, I didn't want to see Intel crash and burn because we sold billions and billions and millions of dollars of their stuff. It would not help us to have an entire generation of their chips immolate themselves, not to mention the user because, if you set fire to the user, there aren't a lot of repeat sales. So we tried with no success. Actually, what it got was when I explained that the scaling of chips was at an end, what happened was the next year I got a phone call. There's something called DAC, Design Automation Conference. And the fellow who had been in the audience at that time, the CTO of Intel, actually put my picture up, drew a red circle around me with a bar across me, said, "Ban Bernie." He says, "Scaling stops." Yeah. And about 6 months later, they canceled their entire Prescott line because it would catch fire. Now, yeah, he's not there, by the way. I did, by the way, there's a the good part of the story, there's a guy named Cheng Meng, who's an Intel fellow, who sat down, did the math, said, uh-oh. So I actually got a written apology from their chairman, followed by, of course, didn't help, they still couldn't build their chips. The chips were supposed to go from 4 gigahertz to 10 gig. Yeah, at 2.4 they melted. Oops. So the laws of physics actually are the same. The other thing you don't know is Moore's law died at that time, as we accurately predicted. If you study something interesting, which is the actual speed of a thread in a microprocessor, it's been pretty much flat for a decade. A decade. This has been dead a long time. Now, Gordon's law, when you simplify it to just more on a chip, that continues. And there's been progress. You can do more if you put more stuff on a chip. But the actual performance through a thread has been relatively constant. So in spite of spending $10 billion to build a fab, there's no more real performance. That era is over, which is really, this is not a little problem. This is a very small problem, in fact. The funny thing is, a generation of scaling in the past got you about 20, 30% of performance. The joke is when you scale something now, things go to hell. So what happens is, if you just follow Moore's law and you don't pay attention to the new requirements, you basically die. So instead, what you have to do is you have to do a huge amount of innovation to recover from the fact that things don't behave anymore macroscopically. When you do that, the last generation of technology, 22 nanometer, this cost about $2 to $3 billion to make one damn transistor. The second one was really cheap. That first transistor was really expensive. And it's much worse now. I mean, the new fabs people are building are between $5 and $10 billion. And this is why when I started in this business, there were about 300 sort of leading edge foundries. And today you've got roughly 4. There's a reason this place has imploded. What's happened is fascinating. Over the years, you have these transitions where for a long time you have incremental progress through electromechanical, mechanical, vacuum tube, discretes, integrated circuits. And what happens is those eras basically are continuous innovation. Somebody asked about a slide. I have a fun slide on this. Continuous innovation is important. The aha moment happens like in '56, we invented the disk drive. The continuous innovation, those long straight lines, is when you then every day come to work and improve it. People tend to make fun of the folks who do that. You're just iterating. So I always enjoy pointing this number out. A bunch of you are carrying laptops. Some have, half a gig, terabit drive, 500 gig or terabit drives. Do you have any idea what your laptop would weigh if we didn't continuously innovate? If we just, invented the drive and said, well, we got the disk drive, let's move on. Do you have any concept of what your laptop would weigh today? Yeah, how about 250,000 tons? That's what your laptop gives a whole new meaning to permanent press. The bottom line is, you have to be willing to value both types of innovation, discontinuous and continuous. The continuous innovation shown here is very impressive. 6 orders of magnitude of progress were made for the integrated circuit so far. The trouble is, at each of these points that are circled, these are the discontinuous innovations, like the invention of the integrated circuit, which was basically done in Texas Instruments owns that one, the transistor, Bell Labs, etc. The problem is at the north end of that, there is nobody who has a viable commercial product today that replaces silicon as a semiconductor. There are lots of things being experimented with, and they're worthy experiments, but replacing it on a generic basis isn't happening for the simple reason that you can make 5, 10 billion transistor circuits and the things work all the time. That's a pretty high bar because you can parallel process through that. Most of the things people come up with that are very, very fast, you can make 6 of them, not 6 billion. And that is a limitation. So you got to be a little careful. What's happened is fascinating. Because of that, a lot of companies just bailed out of silicon because they can't figure out how to get more out of it, and the investment doesn't justify what you do with it. What I found fascinating is what happened in Japan, which is a bunch of Japanese manufacturers like Fujitsu and Toshiba, They basically got out of technology, but you have these huge clean rooms. What do you do with it? So they decided to actually grow lettuce, because you see, you can grow very high quality lettuce without there are no bugs. You don't have to go spray them with anything, no insecticides. It's fantastic. So you have very pristine lettuce. I was just baffled till a friend of mine explained what they've engaged in. That was Moore's Law. Yeah, I wish I could take credit for that. Actually, no, I'm grateful I didn't. But it is fascinating. You know, the world is a very different place when they're growing lettuce inside of one of these fabs. The interesting thing is there is a tectonic shift underway in technology. And first and foremost, silicon transistors will dominate for the next several, literally decades, but they contribute almost nothing. We also have some unique problems. Light is way too slow. 186,000 miles per second is a pathetically, or 3 times 10 to the 8th meters a second, is a pathetically slow velocity. That doesn't sound like a very realistic statement until you understand that the frequency at which we run our chips, you're getting up above 5 gig. A beam of light goes about that far. Meanwhile, people like to build data centers that are 10 times the size of this room. So if you have to communicate across it, do you have any idea how many thousands of machine cycles are lost? Because it takes a long time to get there if this is your hop size. It is a huge problem. The other problem, of course, is you have to come up with new system architectures. If the chips aren't doing it, you got to find other ways to get progress, because you did get a factor of a million just out of the technology. Well, that ain't going to happen anymore. So you better get very creative in a rush. The other thing is, cloud, which is a new architecture, it's really not new. Vital, yes. New, no. The comedy is when I started in this business, you sat in a room, you had essentially a thin terminal that reached out to something which was a shared asset and then sent you back your results. They used to call that a mainframe. The joke is we've come full circle, except that the difference is sitting in the cloud, you have a diversity of systems. It is, what goes around comes around. And by the way, cloud is vital, it's just not a new design. When you have this opportunity to do all this work, I'll give you an example. Light has to go faster. Unless you work at CERN, can't do math, and have a bad day, light isn't going any faster. So you might as well find something else. And when that doesn't work, better make, you can only do 2 things to make a trip faster. You either go a shorter distance or you go faster. If you're not going faster, make the distance shorter. You've already seen this, where people are squeezing what used to be an entire racks down onto a single card. But what's happening long term is 3D, bonding, where you take what would be an entire rack's worth of chips, you thin them to 50 microns each, you bore holes in them, you connect through them, and then you try to figure out how to cool this thing, which is no small feat. In fact, nobody's really done a good job yet. But what's going to happen is you'll have all of this work going on where you go up from the level of the base transistor to system in a chip, and I mean literally system in a chip, and then you go from there. There's a huge amount of innovation that goes on. This is only one of those issues, though. For instance, cloud, why is that important? Because it's a new architecture that, again, will buy you performance, at least what looks like performance. It's just not at the chip level. And it has huge issues. It's just not something necessarily that is fundamentally new, but nonetheless, it's absolutely important. And for a whole variety of reasons, scaling, economy of scale, agility, accessibility, all these other great things. I don't think this is news to anybody here, so I'm not going to dwell on it. But again, it's not technology per se. You can cobble this together from any host of technologies. The difference is, there are people out there who have their laptops, their notebooks, everything else open. You're probably using 0.1% on average of its capabilities. And if you have a well-done cloud where you share things, you might get it up to 20, 30%. So you're talking factors of 60, 100, 200 improvement in the actual efficacy, the utilization of your asset. These are not small numbers. You talk about factors that involve 3 digits, it gets impressive. The interesting thing is, though, at the very moment that technology has really hit a wall, and by the way, they admit it's hit a wall. Intel finally kind of grew up and said, well, yeah, quantum mechanics, it happens. Rhymes with, never mind. The bottom line is, having realized that, there's a double-edged sword, which is at the time that we're sitting here going, okay, I don't really have another factor of 10 to the 6 that's coming. We have a small detail here, which is the rate at which the amount of data we have to deal with is growing has gotten almost out of control. And most of that data is in a form that's not easily handled, it's unstructured. But the really sobering part is roughly 90% of the data in the world was created roughly in the last 2 years. It gives you some idea how fast things are going, because the Earth is what, 4 billion years, give or take? Yeah. In the last 2 years, most of the data was generated, 90% of it, and it's just going to accelerate. If you don't believe that, go look at the size of a data file if you need an MRI or a CAT scan. It's just vast amounts of data, which we didn't count before because, nobody was digitizing it. Well, I got news for you. The electronic medical records require that you store these images lossless, very high definition. And so it's going to get worse. And so at the moment that things are getting ugly, we have the least historical precedent for how we're going to get horsepower. All right, so why do we really care about this? Why is this so vital? So I'll give you a couple of examples. This is one of the earliest big data projects we undertook. We called it Data Baby. It was done with the University of Ontario and a hospital called Sick Kids Hospital, Sick Children's Hospital. I actually once complained to the people doing this. I said, how the hell, big sign says Sick Children's Hospital. Don't you think this is a little dispiriting? Then they pointed out at trees preemies who can't read, so I gave up on that. The point of the exercise is preemies suffer from a phenomenon caused by a nosocomial infection, a hospital-acquired infection, which is called baby crashing. What happens is you'll be looking at this child, they'll be in an intensive care unit, NICU, and they'll look healthy, dead. And there is seemingly no warning. Literally, the child just crashes. The phenomenon is because unlike, you're an adult, well, most of you, I'm sorry, when you come from my generation, moving right along. My kids are older than you guys are. The fact of the matter is, when you get sick, you of course are not showing signs of the infection. It is your immune system that causes you to sneeze and wheeze and have a fever. It's your reaction to it. If you have a highly underdeveloped immune system, you show no symptoms until that disease overwhelms your organs, by which time it's an unrecoverable disaster, and that's what baby crashing is about. This has been maddening to the physicians. Absolutely, imagine what it's like. So we agreed, we said, look, we'll take all the data generated off these systems that monitor these kids. They took incredible amounts of data, to our amazement. You could actually take about 2,000 data points a second. We took everything. And we kept it till hopefully this kid basically went home healthy. In the cases where these children died, we backed up through the data saying, what did we miss? Because, we need more warning. If this kid's septic and they have a viral infection, a bacterial infection, antibiotics, antivirals exist, but on a kid, they're harsh drugs. You don't want to just, broadly inject every kid in the hopes you save one, but you kill 18 by the side effects. So what we did was we just monitored, and to our amazement, if you use advanced analytic tools, when you backed up, you saw some very subtle effects no human could see by yourself. For instance, the heartbeat that the child had was in the normal range through the entire time, right until the heart stopped beating. But it didn't vary as much as it normally would if the child was healthy. The rate of variance slowed down. There were also changes in the way blood oxygenation tracked the heart rate. These are incredibly subtle second, third order effects no human could see. A system of analytics had no problem. So you could build a warning trigger, 24 to 48 hours ahead of this child showing any symptoms. So you did have an early warning system. And again, this is why you need the ability to handle big data. This is why you need the tremendous processing power you want in order to achieve this. In business, it's no different. We work with Statoil. These oil platforms, believe it or not, take 90,000 man-hours to do one cycle of optimization. 90,000 man-hours. The problem is if you don't coordinate well, if you shut one of 40 offshore platforms down, the 39 behind it, 2 of them may be actually unable to produce because they share assets with that first platform. The other problem is you have pumps on the seafloor that may cost you $5, $10, $20 million. How do you know you really need to replace it? Because there's a broad spectrum of lifespans you would expect. What if you could actually measure when this thing is going to die and predict it accurately? Okay. This is something that actually could be done. We went through this. We did a full in-depth analysis. You look at the vibrational patterns from the pumps. You look at the historical data. You see where the vibrational attributes correlate to a near impending failure. You go through all of this, and then you operate for a while. And we couldn't agree on what we had saved these guys. So we called in an independent third party with forensic accountants, the Norwegian Oil Industry Association. They came in, and we had a meeting, and it was quite amazing. They walked in. They said, we're going to make Statoil really happy, but I think we're going to make IBM really unhappy. Okay. Turns out they estimated we saved Statoil $50 billion in the next 5 years. 50 billion US. I think we charged them almost $3 million. It was yeah, we might have underpriced that a bit, but you understand the point. This is a tricky one. This is Freetown in Sierra Leone during the crisis, the Ebola crisis. We have a research lab in Kenya, Nairobi. What we did was we took anonymous data because people were nervous to tell the government about it where the disease was prevalent. We took anonymous data, we analyzed it, and we gave the government every day a heat map saying, look, if you're going to take your precious few resources and send them places, these are the hotspots. Where red is you have people who are literally dead and need to be picked up. There are places where you need to supply chemicals like chlorine to sterilize sheets that have been used by an infected person. I mean, you name it. There are places they don't have electricity, but they need it because they're using it to treat people with artificial life support. I mean, whatever it was, this is something which you can only do if you have enough data, people willing to share it, the ability to anonymize it, because a lot of it came in anonymously by SMS, and trust. We managed to get all of them together, and this was stunning. I showed this 2 years ago at the government summit in Dubai as a guest of Sheikh Mohammed, the ruler of Dubai. They have about 4,500 world leaders there. What I didn't know is one of the people in the audience was in fact the ambassador from Sierra Leone. You never saw a happier individual ever, because this did help. It doesn't cure, Ebola. What it does is it gives you a better weapon. Being able to handle large amounts of data and process it is an issue in everything from just the most basic issue of life support all the way, of course, deeply into business. It is the new oil. If you don't process it, it has no value at all. If you process it, it'll run the world. I wish I'd said that, but I didn't. That's actually from Ann Wimblad of Humboldt Wimblad Ventures. But that's actually pretty much the view of the world today. Now, I gave part of this talk at, of all places, Black Hat. Everybody know what Black Hat is? Right, it's sort of the World Hacker Conference. Believe me, I didn't have a tie on. I was wearing jeans, a t-shirt, and I was overdressed. No, I don't have sleeves. By the way, that's tattoos from here to here, but about half the audience did. It's a different bunch. I'm adaptable. I grew up in the Bronx. But, cyber is like literally the coming unfortunate, horrible next moment. As you guys undoubtedly know, the Ukraine was taken out by a bunch of guys who figured out that you could actually hack into their main system, and their main power distribution system was unprotected. You could literally tell all the substations in the system to do two things. First, open all the relays feeding power to the entire part of the nation. Second, erase everything, which it did. And they were left in the dark. Massive physical destruction with absolutely no shot fired. And then, of course, you got the Stuxnet virus, which basically said to the centrifuges, the nuclear centrifuges that were in use in Iran, you're running 2% slower than you should be. So it turned up 2%. And then they said, no, you're still 2% slow, until they turned them up to the point they exploded. I mean, these weapons are real weapons that do real damage. In the computer world, there are stunning examples of people ripping off tons of money without ever holding a gun. Somebody, basically an inside job, populated $45 million into roughly 15 accounts in a bank in somewhere in the Middle East. Then they printed 3,000 or so uniformed debit cards against these accounts, where only 15 were unique, just many of each type. And people simultaneously, all over the world, went to ATMs and withdrew the maximum amount of cash allowed, and they'd already raised that limit for these accounts. And they drained $45 million of cash from the bank in minutes. Never took out a gun. And the bank didn't notice that you had people in Zurich, London, and New York with the same name and the same password, all withdrawing money at the same time, and no alarms went off. You think you might have had some more intelligent system watching. Okay, cyber is an incredible threat. They estimate roughly $500 billion is currently lost to cyber. I think that's a tiny amount because most people are too embarrassed when they get ripped off to admit it. But $500 billion, that's pretty soon it's real money. Part of the problem is people try to isolate different parts of the system. That doesn't work. If you're going to go after cybercrime, you got to go after it holistically, because any one of those things could be connected. People come in through your telco system, they actually get into your financial system. If you don't have all aspects, because remember, there was an insider at the bank who had set up these $45 million of bogus accounts. He knew that at the end of the day, they would catch it when they did the audit. But by the end of the day, the money was gone. They caught it. There were 15 bogus accounts that used to have $3 million each. Not anymore. You basically have to do this and get actionable insights and correlate this. We've actually built systems now that are just coming online that actually are capable of finding 6 folks connected through hops where they're trying to hide from you. But it requires looking at spectacular amounts of data. Once again, it comes down to we have to find means to extend our capabilities beyond just counting on a bunch of CPUs. They will not give you this kind of performance. So this is the era of exponential change. And just as an example, I'm just going to pick one of them, top left. That is basically becoming sort of a new standard that a lot of you are probably already familiar with. In the past, it was a CPU and storage. Right now, if you don't have some sort of accelerator there, you're probably leaving a lot on the plate. For instance, if you do Black-Scholes simulations for the financial industry, an FPGA will run them 10 to 100 times faster than a CPU because you can run massively in parallel. A GPU does great vector processing. A CPU is terrible at that. Again, it is vital that we look at ways to do things much, much, much more efficiently. And that architecture in the top left is a tremendous challenge. Why? Because people know how to program a GPU, but cooling the damn thing, you might have to pour water on it. Not to mention they're hugely expensive. An FPGA, which is vastly more efficient and way less expensive, the problem there is nobody really knows how to program it effectively autonomically. It takes real skill to write the code. So everything's got its upside and downside. I will tell you this, though. Intel made a bet. I don't know how many people here know. Intel bought Altera. They spent like $11 billion to buy one of the world's largest FPGA companies, and within a matter of years, every Intel processor will have an FPGA. Why? Because you ain't getting nothing out of the CPU, folks. It's going to come from architecture and accelerators. So the world is very, very different today than it was in the past. Now, you can also do some pretty radical stuff in architecture. I wanted to get to this. This is basically a typical system, which is you have a CPU and memory, right? So the equivalent in a human brain would be neurons, a bus, and synapses. The only thing is if a human being was architected like this, you'd be dumber than a brick. The reason is you run at kilohertz. That works okay when you're running at gigahertz. So you're a factor of 10 to the 6 short of being a full loaf. That's worrisome detail. Here's the good news. We're not architected this way. Human beings, of course, run at very low frequency, but massive levels of interconnection, unimaginable compared to a system like this. What would happen if you re-architected computers to run that way? So a guy named Dharmendra Mota, one of our folks out at Almaden, did exactly that. He built the first neuromorphic processor, and then he built one honking big version of it. The basic idea being every one of these things behaves like a synapse, and you essentially can communicate because of the connectivity from literally any one of these cores to any other core. It's not clocked. It's just basically asynchronous clock. And this is actually what he built. It's huge, 64 by 64. It's called True North. This chip is something in excess of 5 billion transistors. And it turns out, because it's running at extremely low frequency, the power needs are almost nil. So you can do, because of the interconnection and the design, some astonishingly complex computation at extraordinarily low power. It is a long way. He first demonstrated with literally one core. He's now up at 4,096. And it uses, well, let me just show you the numbers. This is what it looks like when you package it up. It's called a neuromorphic system. It's about 5 billion transistors. This is the test circuit. There's only one type, so we have the actual True North chip in that socket. Everything else is traditional silicon, because you have to put the data somewhere, and we're not going to go redesign every chip in the world to do this at first pass. This is what it can do. And it's astonishing. It literally, you can teach it to recognize objects dynamically. So what it does is it will recognize the bicyclists, the pedestrians, cars in the picture, buses, you name it. And it does this at a power level that is inconceivable even in the most modern of technologies. It does this at a power level where 2.5 watts. If you want to do true full video recognition in a system where you've got numerous different things you're trying to recognize and they're in motion and they come in and out of the picture, you're looking at something closer to kilowatts than this sort of 2.5. This is incredibly important. For instance, in security right now, they bring all the video back to a central place and you have to stare at it. Imagine if you only brought back video that's identified in advance as being critical. Well, you can't put a kilowatt server out to sit there with every camera. That ain't gonna work. But you can embed with the actual camera chip, a neuromorphic chip at 2.5 watts that does the same thing. It is amusing. My friend, to point this out, he took an infrared camera. He said, let me point out the difference between a neuromorphic and traditional set of chips. And that's kind of obvious. The thing glowing white on the right is a CPU. It is pretty damn impressive. And it's a new way of thinking. And that's really all the point I'm trying to make here. You need to get way out of the box. All right, we are way past just, do the same thing. And the saddest thing about Moore's law is people just kept somehow stopping us from going forward by assuring us incorrectly that this will go on forever, so don't worry. There's another factor of 1,000,000 here. We're looking right now at maybe another 2 or 3 generations and a factor of 0. There's no upside. The threads will remain the same speed. Yes, you'll put more on a chip, which means effectively it's like you have more chips to do the work, and that's not a surprise. So it won't stop scaling. It'll get smaller, it just won't get any better. And that's worrisome because, like I said, we got a factor of 1,000,000 and we're not looking at another factor of 5. Now what? So, just to make sure that things are getting worse, that is, believe it or not, that's an architecture of an application in a major bank. Okay, inside each of those boxes can be an architecture that's as complex as what that looks like. We call it a spaghetti diagram. Again, we are getting to the point where the complexity of what we're trying to analyze has exceeded a human being's ability to deal with it. This thing was actually dying about every 3 months. This is a global architecture. It would go thud. And they never could find out why. And I brought a mathematician down. We have one of the largest, if not the largest, non-academic math department. We've got about 400 PhD mathematicians. And the reason is, to do this, again, it's about analytics. Get the data and analyze it. It's not about hardware. And this mathematician, Orly Lozano, there's something called Granger Causality. It's the ability to back up through something that's occurring and extract with rigor what causes it. The problem is, in a problem like this, where you don't know how long it's been since the system started to have trouble or where it was, you're looking at so many things going backwards in time that if you just look at everything, it explodes. The math is impossible to do more than a few seconds back. She actually rewrote the algorithms for Granger's causality to chase just the most likely paths. Discovered that something like 60-something minutes before this system crashed in New York, a server somewhere out in Europe went down, dropped its load onto 2 other servers whose basic utilization of memory went slowly to 100%, at which point they start paging, which means they basically stop. And slowly this cascade went around the world. It'll hit New York. What was more amazing is she did this in a span of only 2 weeks because we were sitting at the table with this bank and she said, look, Granger causality won't work. I'm going to have to rewrite all the algorithms. And anybody who knows about this, those techniques were around for decades. And I said, Orly, how long is it going to take? She said, well, it has to take less than 4 weeks. I said, why? And she stands up and she was going to deliver in 4 weeks. So I'm not that observant. But nonetheless, she got it done in 2. The point is, great innovations sometimes come from just problems like this where complexity has started to overwhelm us and you have to develop technology to address it, even if that technology is just math. The thing is, human beings are beginning to get outscaled by what we've created. This is where AI comes in. And before somebody says artificial intelligence, please, I worry a lot about that term. It has a huge amount of baggage, not to mention if you look in the dictionary, the word artificial is defined as fake. And you don't want fake intelligence because that's stupid. So let's try another, I'll call it augmented intelligence, accessible intelligence, call it what you want. The other problem I have with AI is, of course, when you say AI, everybody thinks of either Terminator or the HAL 9000 in Space Odyssey 2001, which if you've ever seen it, it says those famous words, "Good morning, Dave," as it's murdering all the humans on board a spaceship. I don't need friends like that. You don't need enemies. By the way, please tell me you actually understand where that came from, HAL 9000. If you didn't, do this favor. Right-shift each letter 1 letter. H becomes I, A becomes B, and L becomes M. The IBM 9. They actually came to us, believe it or not, and wanted us to let them name the computer that murders everyone, the IBM 9000, and we politely declined. So they just left shifted it one letter and said, all right, we'll call it the HAL 9000. Everybody will know it's you anyway. Thanks a lot. Okay. Yeah. Let's just keep going. All right. So what happens here? You've reached the point where human beings can do a great job, but you know what? There is a limit in the complexity you can handle. And so what we've really progressed from is originally the tabulating systems, programmable. We're actually now in cognitive systems. These are systems that are intelligent enough they seem to think. Take my word, they don't. But what they do is they scale your capabilities, because you as a human are not going to sit there and crawl through tens of thousands of articles, weight their importance based on a number of factors, not to mention the history of your guessing answers from them, and come back and say, by the way, you should do this with that to get an answer that is going to be right. And by the way, here's what I think the answer is with this probability of being accurate. The fact is, they're unique because you teach them. They are taught, there are algorithms that are learning algorithms, and you can train the system, and that's the difference. You don't program it. It's not, there are many systems today that pretend to be AI, but they're actually just scripted. What they do is they write down every question they think you could ask, and they spit out pre-written answers. Okay, that is not AI in the sense that we run something like a Watson. The way it works, just to give you a rough idea, is you get a question, you decompose it, you generate hundreds of hypothetical answers from that question, but then you start measuring those answers against vast amounts of evidence. And you don't store, by the way, raw data. You also store knowledge. Literally, you store findings, so that you don't have to necessarily look at 10 billion things each time you do this. You may already have some essentially pre-calculated elements, and the system will dynamically weight that information for accuracy based upon how successful it is in a prior effort to get you an answer. And what you eventually get out of these learned models is you get an answer with a probability that that answer is successful, and you'd be amazed how accurate that can be. And that's really the key to this, is this system has access to unimaginable quantities of data. You bring your compassion, your intuition, your gut sense, which no machine has, but it brings the ability to scale, which you do not have. I don't care how good you are. You don't suddenly say, I'll read the 18,000 textbooks on the subject today and we'll work on the answers. That doesn't work. So you need both. You need human and the systems. I'm going to give one example because I want to leave some time for questions. We did this work with Memorial Sloan Kettering. It turns out that what I'm going to show you is a video that we had no part of. It was done by Bloomberg. And Bloomberg News interviewed a bunch of the guys we were working with. And what it explains is sort of how they utilize the case where you have an intelligent system jointly with a physician in the instance of working in oncology. So with a little bit of luck, so far so good. I didn't tell you, this is the first time I've actually used this new machine, so.
Watson, who is David McCullough, correct?
IBM's Watson, the technology that beat 2 humans on Jeopardy 2 years ago, may be the technology that helps doctors beat cancer. Dr. Arthur Forney at WestMed Medical Group in New York is testing Watson in the form of an iPad app during its pilot phase.
So here Watson was given a very unusual case, a young Asian woman, non-smoker, who has lung cancer.
So now you tell Watson to do its thing, and it's now looking at the data you inputted, the data from her imaging, from her biopsy.
In 17 seconds, Watson has analyzed about 3,500 textbooks and 400,000 other pieces of data.
This is the screen where it shows you that after looking at what you have so far, it would consider that you would do several other things for the patient that it doesn't see yet in the chart.
In an instant, Watson has figured out what caused this cancer.
It turns out she has a very rare genetic mutation, which is accounting for her cancer.
And offered 3 treatment options.
It has shown that treatment 1 has a 95% confidence of being effective, whereas treatment 2 is only half that.
Is this so obscure that you would have needed Watson for the diagnosis and treatment, or would an oncologist come up with the same treatment plan?
In fact, this is such a new discovery of this particular mutation.
Okay, I don't know if you saw those numbers. This thing looked at about 500,000 journal articles, 100,000 clinical trials, 3,500 textbooks. Now, it's not that it read them there. It had already ingested them. What you do is you train a system like this with a corpus of knowledge. But that corpus of knowledge is accessible to it at blinding speed. It's not that it displaces the doctor. Like it said, somebody discovered and wrote an excellent paper that there is a genetic mutation that is associated with the observation that people have a proclivity to this particular cancer. But that paper had just come out. Do you know what the average physician reads? How many papers the average physician reads in a month? About 5. About 5. You're not going to crawl through literally 250,000 in a lifetime. Not in a lifetime. So this doesn't replace the physician, but what it does do is it not only says, hey, this is relevant to your decision, but here's what I think you should do, and let me show you the background material from which I garnered that decision. The other thing is it will make mistakes. It is perfectly normal for it to, during one of the games we played with Watson, it was said, name an American city with an airport named after a World War II battle and a World War II hero. Okay, so it promptly came up with Toronto. We annexed Canada. That's okay. The Canadians, meanwhile, are threatening to build a wall, but that's a whole different problem. The interesting thing about it is the bottom line is, remember, Canada is in the Americas. It's a little subtle. It took American and Americas as the same thing. Therefore, hey, Toronto seemed reasonable. The number 2 answer right behind it, by the way, was Chicago, O'Hare and Midway. Famous, war hero battle. So these things, that's what I mean by training. You have to go back in and say, no, American is USA, whereas Americas is, oh yeah, the entire Western Hemisphere, It's not perfect, but it is remarkable that we've got systems that get that far. And as he said, there's no chance in hell a physician would have seen this. Not that they're ignorant, not that they're slouch, none of the above. It's not a criticism. You know what their problem is? They're human. Humans have finite capabilities, and you will see now much more of this becoming available. This will be something, these technologies, whether it's in call centers, whether it's in oncology, whether it's actually in any one of the many, many places that you have vast amounts of data which a human themselves can't necessarily scan, these systems will be essentially augmentative, and you will get partnerships with them. And it is astonishing. I've seen it developing, and it's not a replacement. But you get people who, in their careers, suddenly seem to become supermen and superwomen. That's kind of interesting. So, in any case, let me just wrap up, because I'd like to have a little time for questions.
And it's a relatively new drug as well.
There we go. So the bottom line, brute force technology is dead, which is actually a fairly strong statement. It's also true. It's been dead for a long time, just nobody wanted to admit it. There are lots of system-level innovations, however, that will make up for it and dominate progress. They'll just be very, very different. Most of these interesting capabilities, though, and that's the really wonderful part of what's happened in cloud services, these capabilities that used to be unique to big firms are now available to everyone. Because in a cloud format, if you want the thing, go get them. It's all yours. So that is a tremendous capability, in that you can grow a business online, as you guys know, in a matter of weeks that might have taken you years previously. So there's a seminal change in the business environment as well. And it also keeps large companies on their toes. Let me tell you that inside of IBM, I've actually created efforts where they look more like startups than they look like part of a major company, because if you don't move at extraordinary speed, somebody else will eat your lunch. So that's the other thing, is it's forcing organizations to really rethink how they operate independent of their size. Big or small somehow doesn't necessarily have an inherent advantage. You just have to go like hell. So in any case, thank you very much for your time and attention, and anything you want to heckle on, here's your grand opportunity. I'll do the first one. That's why we have the machine. It actually is a mix. It actually has both analog and digital components. Inside that CPU, there is actually a small CPU. Inside each one of those neurons is, in fact, a CPU. So it's reasonably flexible, shall we say, but no, it won't crunch big-time math. It's not meant for that. It is. Yeah, it's closer to analog than digital from the perspective of it's not clocked. It isn't truly actually analog. The joke is it's digital circuitry, but it's run at a clock frequency would associate with a classic analog system, which is why it's so low power. It's really fascinating, though, and it's a bear to program that's just barely getting going. It's a new field, but it is exciting. And I've been at this for 40-odd years, and I will tell you that it's amazing that 40 years later there's this enormous amount of invention. It really is a discontinuous shift. And I don't just worry about it, by the way, from the technical side. As part of my work in the World Economic Forum, Klaus Schwab, who was the founder of the forum, is warning that this is really the fourth industrial revolution. But each time these happen, you always have Luddites who say, let's break up the materials because this will put everybody out of work. The joke was that the guys who made the leather parts like buggy whips, before the iron horse, as they say, the buggy whip manufacturers, when Ford came along and made cars affordable, said, what's going to happen to us? You don't have to whip the motor. But the fact of the matter was, they of course did all of the interiors of automobiles, which were all leather, except you needed 100 times as many of them. Yes, one thing dies, another thing shows up. And I'm actually fairly optimistic that there will be new fields that will emerge to work with these new capabilities. And so it's really an incredible opportunity. I mean, tremendous. And I've stalled long enough, you can come up with the second question. See, there we go.
We had a gentleman here about 18 months ago, and he came and talked about applying Watson to cybersecurity problems.
Right.
Okay. And at the end, he told us some interesting things. He said one of the big problems is that it learns the wrong stuff. It's a bear. It's almost like the classic science fiction thing where you have to kill the machine and regrow it. In the medical application, all sciences are a set of trajectories with backtracks. Watson's been around before the guy finally browbeat the medical community into knowing that ulcers were actually bacteriological. Watson would make the same mistake, right? So it's limited by the underlying knowledge science.
Sure. I mean, again, it's not a native intelligence, but here's the difference. It can tell you that there's a dissenting view. And that's the important part, because it can look through all of this and say, look, I have 87 things that point at A, but I have 2 that point very strongly at B, and they're outliers. So you may want to look at those. He's absolutely right. The problem is that there's bogus, quote, knowledge out there. You remember Laetrile cleared all cancers. Remember apricot pit extract? Well, no, it didn't. A lot of people died trying this. The bottom line is that after a while it got debunked because the weight of knowledge showed that it didn't work. Watson's not magic. You are right. You can, however, force a correction. One of the challenges, as you said, is, if it learns, quote, the wrong thing, it puts a bias in the corpus of data. But you can also devalue elements in the corpus that have been proven incorrect quickly. So it has come a long way, but it's challenging, I'll be honest. What we have done, and you can all almost play with it now, because Watson was so somewhat profound, we had so many people coming at us, we were drowning in everybody wanted to do everything. A new guy came on board, a guy named Dave Kenny. He was the CEO of the weather company, which we acquired because of the data they have. The ability to get data with the resolution they have and some of the computational capabilities we have, we can basically tell it'll rain on your neighbor's house 2 days from now. Not yours, your neighbor's. I mean, I'm not actually making that up. It's 1 kilometer resolution a couple of days out. Today, 144 square kilometers is kind of the benchmark. But Dave also brought a skill with him, which is how to scale stuff. And he said, you guys are crazy. Just create a platform and let other people do it. So what we actually now have is something called Bluemix, which hosts many of the applications we make available publicly, one of which is Watson. And you can get on Bluemix, and what you do is with an ID, you can pull up and assemble you can literally assemble a function where, okay, here's your text, here's your speech to text widget. You go click, okay, I got speech to text. Here's this corpus of data for such and such, click, all right, I'm going to embed that. And then here's my text to speech output, click. And so you can actually click and build an entire assemblage. Now, of course, my guys, you have to know my team. If you think I'm weird, you should meet them. Of course, they say that about me. But The respect is mutual, as they say, or a lack. And I sent them off to go do this. So they came back with something that found the absolute best beer brewery where for the least amount of money you could consume the most amount of alcohol of high quality. Then they showed it to our chairman. Okay, I'm still here, so Ginny has a sense of humor, thank God. In any case, it is impressive now that you can make this more generally available because we found that, we're not the only smart guys out there. It's the biggest thing that kills most large companies is that they somehow believe they're it, right? And ain't nobody else out there with a brain. Guess what? There are lots of other smart people out there. I'd rather engage them than compete with them. And so we actually did that with Watson to make it much more accessible because other people will have really good ideas what to do with it. Yeah?
With our capability to analyze data today, I sort of wonder whether we've been smart enough to record the right data in the past. And once we realize that we can record everything and we can really analyze it now, might the field explode?
Yeah, the question is very simple. You would think that if we record all the past data and can analyze it, the world of knowledge will virtually explode. The problem is when you can't go back and capture a lot of the data because it's gone. I mean, people held data, but they held it in so many formats and then disposed of it. They were turning over their technology every couple of years. Lots of time they turned it over by basically literally taking the disk drives out and crushing them. So it's not that easy to go way back. But yes, you can actually take data that's been acquired and not understood and do analytics today that it can extract information you would have never had. We did that with predicting important failures of large machines. If I told you what it was, you'd know immediately who this is. But a bunch of my guys were challenged by a manufacturer of massively complicated systems. And they said, tell us we want to know when this thing is going to fail. Because if we know when it's going to fail, we could proactively do maintenance. If it fails, it doesn't kill anyone, but we have to shut the machine down, inconveniences us massively. The bottom line is, it turns out they had years of data on all aspects of this machine, vibration noise, all kinds of heat signatures, you name it. They kept all the data, they just never correlated the data with failures. And it turns out the reason they couldn't find them is you had to see like 6 signals simultaneously do something weird, and then you knew it would fail. But we found with about 80% accuracy, I could tell these guys in the next 24 hours this system was going to fail and what was going to quit. And they would go in and fix it, as opposed to having it break down and have to drag it somewhere to fix it. So yes, there are some limited cases, in fact, where we are able to go back at historic data without getting anything new and just run the analytics. And so it's happening more and more. What I'm hopeful of is, if you want really the exciting next field, the human genome, when I started at this, cost a little over $2 million. Actually, it couldn't be done. But somewheres when they started, it was about $2 million to do a genome. It's now down to under 1,000. It'll shortly get down under $100 to do a genome, which means when you go to the doctor, basically they're going to take your genome, which is kind of just like a blood test. Well, if everybody has a genome and then you say, all right, let's look at people who suffer from this disease because there are 4 different treatments and some work, some don't, but it doesn't correspond to anything we've seen. Then they go back, look at the genetic makeup of each person and what they were treated with and give a plus, and basically analyze if they have this genetic makeup and they had that treatment, it didn't really work. But this other person with the same genetic makeup and this other one of the treatments, it worked great. And to be able to simply tailor the treatment protocols based on knowing your genetics and knowing basically which treatments were efficacious for that genetic makeup would be phenomenal. That would change medicine. Without spending money, new drugs, nothing. Just simply, what do you use? And that's really an interesting part of this. So there's a lot of cases where there is existing data, genomic data, which isn't being used today because A, we don't have it correlated, we don't have enough of it. But that too will come. So this is going to be an incredible field. I mean, you haven't seen anything yet as to what will shortly be coming. So, I don't want to go too deep into this, but there's something called CRISPR, which basically is the first technique that lets you edit a genome. Literally take a gene out from a specific location or put it in a specific location. Right now, genetic engineering is a crapshoot. You basically take a virus and stick a gene somewhere in the genome and hope for the best. This is really a genuine editor. Imagine if you have that capability and you know what each gene does. We're getting there. It's just now starting. There are human trials starting because we know certain genes cause certain lethal diseases. If you edit them out, they don't happen. I mean, we have a possibility. It's kind of, we killed off smallpox, but imagine being able to kill off other inherited diseases by literally removing, I hate to say it, you're going to chlorinate the gene pool. You know, it's really an exciting time. I think I'm a little over time, but maybe one more? Yeah.
One of the issues that you bring up is taking in all the data and examining it. What kind of perspective do you have when in the next 10 years we're looking at all the healthcare data that you just mentioned, but a lot of fragmentation in the system and very little willpower to deliver any kind of API that makes this data meaningfully accessible?
Yeah, this is a classic problem, which is everybody loves to cook their own, cook their own food. Unfortunately, therefore, none of the data is necessarily easily handled. It is getting there because we actually do have now techniques that can sort of universally take unstructured data, which effectively is, if everybody's got different structures, that's unstructured data, and coalesce it into a single visualization. That technique is coming along. There are a series of projects we've had over the last 5 years to take disparate data sets and simply figure out autonomically by looking at them what corresponds to what in a medical record. It's not perfect and it's early, but you're absolutely right. That is one of the great challenges. The other thing that's happened, though, is government regulations are kind of forcing people to get at least some level of commonality on electronic medical records. There are also countries that already have that. Not everybody allows, random guesswork, right? You go to places like Singapore, Iceland. I mean, there are certain places where they said, look, here is the structure of a medical record, period. QED. And those guys will get ahead because they will have a much easier time processing and correlating that data to cause and effect. We have to, we're the United States. We do everything uniquely. The good news is there are some companies that are so big, companies like Epic. We have such huge amounts of data that even if it isn't everybody's data, it's sure as hell enough that you can get a good start. Yeah?
You convinced me that we have achieved a lot and there are a lot we need to do. I guess the question is, why do we need all those technologies? I mean, chips are running faster, phones are smarter, but if you think about a human, are we really much happier than the ancient foragers, hunter and gatherers? I guess, what do you see the future of the technology innovation? Where's the Moore's law leading us to? Is it a crash, or what sort of?
That's a good question. So I'll give you one answer. I mean, as you know, China tried the one-child policy, which has since now been abandoned. Every time you try to change human behavior or human desire, it has very bad unintended consequences where suddenly you have a terrible imbalance of too many men and not enough women because people basically are selecting based on various cultural, ethics biases. These kinds of things, which happen throughout the world, it's not unique to China. Every country has its own version of this. That's the danger when we try to mess with human nature. The problem is if you have a population that's rapidly expanding, what do? It's a damn good question, but you then look at the digital divide. You look at nations in sub-Saharan Africa where poverty is rampant, disease and essentially malnutrition are just the way of life. And then you look at these kind of capabilities. I'm just going to pick one example. If you make something with an AI and accessible intelligence, and that's why I really like that term, accessible intelligence, if you make that available through any input, even voice, which isn't that hard. Imagine you're a farmer living in some fairly desolate area, and you have an option, which is you can literally take your cell phone, which, believe it or not, there's everywhere nowadays, and you call a number, you press a button which says help, and you literally say these words: I need to plant a crop, and I want to know what I can plant that minimizes the chance that my family will starve. Something that basic. A system that's intelligent enough will say, all right, I know where they're calling from geolocation. I know the history of the region. I know the soil conditions. I know the rain that has fallen in the last 6 months. I know if it's a drought or if it's a flood area. I know all of this, and I have 57 new varieties of rice and sorghum wheat that are resistant to various prevalent diseases in the region that actually will work under those growth conditions and the time of year it is. And it will tell that farmer, you plant this specific type of sorghum wheat, which you just can get the seed from a standard store, and you will get a crop that's 70% larger than anything else you could have, and no, your family will not starve. I mean, that's sort of the holy grail, which is to make this kind of knowledge available to everyone. There are all kinds of other societal issues you've got to solve, which I can't solve. But the technology itself can be put to tremendous positive use, and by the way, negative use. We know this. I mean, all technologies go both ways. But if you look at the history of the world, the history of disease, without these technologies, a lot of us wouldn't even be here. So I do admit, by the way, that there's a huge challenge here, because where's the end? But you could look at this as being a case where it'll just eliminate all humans, all need for human work, because most of it will be done by a machine, and there'll be riots. Or you could say it's going to be the golden age of humanity, where we can actually feed everyone. And oh, imagine that. So maybe we do have time to finally fund the arts. Maybe we'll have a Da Vinci-like heyday where people actually have spare time. You don't have to work 70, 80 hours a week. How about 25? Because it's more efficient. I mean, you can cut it both ways. And so that's always the challenge, is to get it right. And I don't propose I have a magic recipe, but I tend to be an optimist that, generally speaking, I've seen, you got to remember, when I started in college, I had did anyone here know what a slide rule is? Yeah, right, it's the geezer fest. It's like me, I had a slide rule. I did not have a calculator. They didn't exist. Okay, so we've gone from that to the fact I've got an S7 here, which has more computational power than pretty much any supercomputer 8 years ago. Okay, so I've seen this, but I will tell you that if you look at today's lifestyle and the fact that we used to eject everybody through the windshield of their car when they hit something, because seatbelts, what are seatbelts? I mean, there's been incredible progress, and there's been incredible downside, because you also have proliferation of nuclear weapons, and I mean, it's always a balance. But I would argue in the whole, that balance has been tremendously positive for society. And it's your responsibility, guys. You're inheriting the future. Don't look at me. You will set the tone. That's why we have educational institutions that are universities and not just colleges. We have them so that you learn not just the technology, but the humanistic aspects behind it. And one would hope that you know better. It is the challenge to you. You raised a great question. Go fix it. It's your challenge. All right, thank you very much, guys. I'm way over time.